So now we're going to start with integers and how we use integers in algebra. And we look on page 48. We're going to break it up into three parts, what we mean or the definition of an exponential expression. Okay. And secondly, we're going to deal with the rules that govern the use of exponents. And then thirdly, we're going to look at the properties of exponents. So this is our first introduction to exponents. So let's begin with a basic definition on the top of page 48. A to the n is an exponential expression. When we write a to the n, we mean it's an exponent. N is the exponent and a is the base. For example, if we mean a to the n, when we write a to the n, we mean a multiplied by itself n times. So if this is a to the fifth, we would write a times a times a times a times a till we had 5 times. We have a to the 3. Okay, that's an exponential factor. We multiply a times itself 3 times. So that gives you a little bit of an understanding. The second rule that we're going to look at now is a to the 0 equals 1. And the third part of this rule regarding exponents is that a to the minus n equals 1 over a to the n. So a to the n is read as a to the nth power. So here I have 2 to the power of 1, here I have 2 to the power of 2, and here I have 2 to the power of 3. Sometimes I say this is 2 squared and this is 2 cubed. So when the power is 2, we use the word squared, and when we have the power 3, we use the word cubed. I could have a to the power of 1, a squared, and a cubed. So as far as part 1 is concerned, supposing we had 2 to the 5th, what does this really mean? It means 2 multiplied by itself 5 times. That's what it means. 2 to the 5th means 2 multiplied by itself 5 times. Another way we could look at it is that each of these 2's is a number. When we write it, is always raised to the first power. That's what we mean. Now we don't put it in, just as we don't put 1x in. We just leave it as x. So there's an implied 1 here. So what we're doing is really adding 5 times these powers to get that. 5, 1 plus 1 plus 1 plus 1 is the same as 2 times 2 times 2 times 2 times 2. So we add the power 1 5 times and it gives us 2 to the 5th. The second part 2 was to show that any symbol, as long as a does not equal 0, anything raised to the 0 power is 1. Any number raised or symbol raised to the 0 power equals 1. Now to remember this, let's just choose a number for a. We're trying to prove that a to the 0 is 1. So 1 is equal to 6 over 6. 6 divided by 6 gives me 1. 6 is 6 to the power 1. This 6 is 6 to the power 1. When I bring this power up, it changes sign and becomes minus. So what I'm doing is, and we're going to get into that a little later, but when I move a number from the bottom to the top, what I'm doing is I'm going to move this 1 up to the top here, and then in doing so, its sign changes. So 6 to the 1 power 1 on the denominator becomes 6 to the power minus 1 on the numerator. 1 minus 1 is 0, so 6 to the 0 is 1. Now replace the 6 with the letter A. So instead of 1, we get a over a, which is a to the 1 over a to the 1, a to the 1 minus 1, which is 0, so a to the 0. And that helps us understand. And here we see the rule number 3 on this page, where if we have a raised to the power minus n, we can change this, move it, this is on the numerator because we're assuming this is divided by 1. If we move it from the numerator to the denominator, it changes sign. So the minus n on the numerator becomes plus n on the denominator. This works for anything as long as a does not equal 0. So the exponent changes sign when moved from the numerator to the denominator, or vice versa. In other words, if I go from here to this over here, I go from the right to the left. I'm moving this from the denominator up to the numerator. It changes sign. Here's some examples of this. X to the minus 2 becomes 1 over x squared. Because what's happening here is the minus 2 is on the top. X to the minus 2 is on the numerator. I bring it down to the denominator, it changes sign. Here, the x to the minus 4 on the denominator is moved up, and the 4 is put, the x to the 4th term is now on the numerator, not on the denominator, so it changes sign. Let's just go back and look at all these basic parts of the definition. Part 1 is that a raised to the power n means that we're going to multiply a by itself n times. Multiply a by itself n times. So if I have a to the power 3, or what we sometimes call a cubed, I multiply a by itself 3 times. We also showed that any number or symbol raised to the 0 equals 1, providing that a doesn't equal 0. And the third part is if we change the exponent, here it's on the numerator, when we change it down to the denominator, we change the a to the minus n to a to the plus n, then it switches from the numerator to the denominator. So a to the n is read as a to the nth power. So if I say a to the 5, a5, this means that a is raised to the 5th power. A to the 1 is the same as writing a. There's an implied 1 there. So we don't have to put that 1 in the same way that we don't put, when we write x, we don't put 1x. A to the 2 is read as a squared, so the number 2 is read as squared, and a to the 3 is read as a cubed. Now let's look at the rules regarding exponents. And we have 3 rules really that we're concerned with. We have a to the power m times a to the power n equals a to the m plus n. And this is called the product rule. The power rule, you'll notice the brackets around here. There's no brackets here. So we just add these powers in this case. In the power rule, we multiply. And we're going to see examples of each one of these. I'm going to show you examples of each one of these rules. Here we multiply. Here we add. And here on the quotient rule, which means that we're doing some sort of a division process, we've got some sort of a fraction here. We've got a to the m over a to the n. This becomes a to the m minus n. I've moved the n from the denominator up to the numerator. Now you'll know that in all these cases, the base must be the same. I can't do this unless the a's are the same here. Same thing here. I can't invoke this rule if one is a and one is b. So the base must always be the same. So let's look at the product rule. Here we see that a to the m times a to the n equals a to the m plus n. So if I have x to the 5, x to the 2, this is equal to the x to the 5 plus 2, which is equal to a to the 7th by the product rule. Excuse me. I have x to the 5, x to the minus 2. I say 5 minus 2 equals x cubed. Minus 5 minus 2, I add these two, minus 5 minus 2, I get minus 7. X to the minus 5 plus 2, I add minus 5 plus 2, and I get x to the minus 3. So this is the product rule. Now the next rule is the power rule, and here I'm raising something to the power. So, for example, I'm saying x to the 5 power to the power 2. Here what I do is I multiply these two numbers together, m times n. This is the power rule. Okay, so 5 times 2 is 10. 5 times minus 2 is minus 10. Minus 5 times minus 2 is plus 10. And minus 5 times plus 2 is minus 10. So the rules here are the same as obviously for the rules of the multiplication. If the two m and n have the same sign, the answer is always plus. If m and n have different signs, then the answer is always negative. Now here we see the quotient rule. A to the m divided by a to the n gives me a to the m. When I bring this from the denominator to the numerator, I change the sign. And the proviso is that a does not equal 0. So here I have x to the 5 over x to the 2. I bring the x to the 2 up, and I get minus 2. 5 minus 2 equals x cubed. Now remember what I said, these two must be the same. I can't have x here and y here. It doesn't work that way. They have to be the same variable or symbol here in order to use the quotient rule or any of the other rules. I have 5 x to the 5 over x to the minus 2. This becomes x to the 5 minus, because I'm bringing this up to the numerator, and then it has minus 2 in front of it, so it becomes plus 2, and that's 7. I have x to the minus 5, and I bring this up, it becomes minus 2, minus 5, and minus 2 is x to the minus 7. And finally, here I have a minus 5 and a minus 2. Minus 5 stays the same. I bring this up, and I change its sign. Minus minus 2 is plus 2, so I have minus 5 plus 2 equals minus 3. So on the quotient rule, you can see whenever I bring something up, although I've done it in steps here, really I said minus because I brought it from the denominator to the numerator, and then it already has a minus 2 in front of it. So minus minus 2 is plus 2. I could have just said, okay, bring this up, make it a plus 2. Bring this up, make it a minus 2. Bring this up, make it a plus 2. Bring this up, make it a minus 2. So you can do it either way. This is just sort of an explanation here. So what we've done is the product rule. And you'll notice here on the product rule, we have both bases shown here, so we just add these. Okay, here we have the power rule, and there's a bracket, and here we multiply the m times the n. And here on a fraction, when we bring the n up, it becomes minus n. So finally, let's take a look at some properties, and we should be able to, we're going to do lots of examples of these. And what we're going to do is should be able to move each one of these properties from one side to the other, or move them from left to right or from right to left. In other words, you should be able to recognize that ab to the nth power is a to the n, b to the n. Or if I give you a to the n, b to the n, you should be able to write this. So we'll go into each one of these individually. A over b to the nth power equals a to the n over b to the n. Here what happens is a to the minus m goes down here, b to the minus n goes up there, becomes positive. That's rule number 3. And here a over b to the minus n equals b over a to the n. So let's look at each one of these. A, b to the nth power really means a to the 1, b to the 1, and I'm sorry, this should be a full bracket here, raised to the nth power. So when I multiply the 1 times the n, I get n. I multiply this 1 times the n, I get the n. So we're using the power rule here. For example, here I have ab to the 5th power. There's an implied 1 above the a. There's an implied 1 power above the b. So I'm going to raise 1 times 5 gives me a to the 5th. b is b to the 1. 1 times 5 is this. So I should be able to go from this expression to that expression, or take this expression and write that. It'll depend on the situation, but you should be able to go from the left to the right and from the right to the left. Here's an example. Supposing I had A 12th, B 9, C 3. I could write this using the power rule as A, put a bracket around the ABC, and then realize that a to the 4 times 3 gives me 12, b to the 3 times 3 gives me 9, and c raised to the power 1 times 3 gives me 3. So this term equals this one, or this one equals that one, and this is application of this rule. Now you'll see here that I have a to the minus 3, b to the minus 1, minus 2. By the power rule, I multiply the minus 3 times the minus 2. The minus 3 here times the minus 2, I get 6. I multiply the minus 1 times the minus 2, and I get plus 2. Similarly, over here, a to the power 3, by the power rule, when I multiply the 3 times the minus 2, get minus 6. Minus 1 times minus 2 gives me b squared. So just look at those and just make sure you understand them. Here, for example, under the second rule, if I have a divided by b to the nth power, this is the same as a to the 1, b to the 1, because there's an implied 1 above the b as the power, and a is raised to the power 1. That means this is the same as a over b now to the nth power. I multiply 1 times n, I get n, and I multiply the 1 times n here, and I get the n here. So this expression right here is equivalent to this one. So if I wrote a over b to the 5th power, There's a 1 here, 1 times 5. As I said, this is 1 and this is 1 here. That's implied. Multiply 1 times 5, I get a to the 5th. I multiply the 1 times the 5 here, I get b to the 5th. So this expression and this expression are equivalent. If I multiply minus 2 times minus 3, I get plus 6. If I multiply minus 3 by minus 3, I get b9. Over here, 2 times minus 3 gives me minus 6. Minus 3 times minus 3 is b9. And here, what we've done is move the a minus 6 from the numerator to the denominator. The b9 stays where it is. Now, the reason we do this is that for most cases, we usually leave the answer with positive exponents. We try to leave whatever solution we get, we try to leave it with positive exponents. Now, the third in our list of properties says that a to the minus n over b to the minus n equals b to the n over a to the m. So what you're doing is taking the a and moving it from the numerator to the denominator. It changes sign. You move the minus n, b to the minus n, move it to the numerator, it changes to b to the plus n. So this goes down here and this goes up here. So the a minus 3 goes down, becomes a plus 3, a raised to the power 3. B to the minus 2 on the denominator here becomes b raised to the power 2 here. So if we have a to the minus n, and b to the minus n, we could just flip this. And so what we can do is just say this is 1 times minus n, gives us a to the minus n, then move that down here, or just move the a down because this is raised to the minus n power, and flip this here. B becomes where the a is and the a becomes where the b is, and we get ba raised to the power n. We make it positive. We change the minus n to the plus n by flipping this. Now in this case here, let's take a look. Let's say that we have a over b to the minus 3. This is a to the 1 over b to the 1 times minus 3. So here we see that this 1 times minus 3 becomes a to the minus 3. 1 times minus 3 becomes minus 3. Now we're going to flip this, put the b minus 3 over here, and becomes b cubed. The a minus 3 here becomes a cubed, and now we can write this as b over a cubed. So a over b to the minus 3 becomes b over a to the plus 3. And that's what we've done here, and we've just done it stepwise. So we're using minus n, we're using minus 3, n becomes 3, and the fraction flips. And if you look at this stepwise, you understand the reason for this rule.